Making of semiconductor chips. In this lecture, we are going to discuss important steps for making integrated circuits, starting with sand. The first step is converting sand into silicon ingots. Sand. Silicon is the second most abundant element in the earth crust. Common sand has a high percentage of silicon. Silicon, the starting material for computer chips, is a semiconductor, meaning that it can be readily turned into an excellent conductor or an insulator of electricity by the introduction of minor amounts of impurities. Melted silicon. In order to be used for computer chips, silicon must be purified so there is less than 1 alien atom per billion. It is pulled from a melted state to form a solid which is a single, continuous and unbroken crystal lattice in the shape of a cylinder known as an ingot. Monocrystalline silicon ingot. The ingot has a diameter of 300 mm and weighs about 100 kg. Now we are going to discuss how the ingot is converted into wafers. Ingot slicing. The ingot is cut into individual silicon discs called wafers. Each wafer has a diameter of 300 mm and is about 1 mm thick. Wafer. The wafers are polished until they have flawless mirror-smooth surfaces. Intel buys manufacturing ready wafers from its suppliers. Wafer sizes have increased over time, resulting in decreased costs per chip. When Intel began making chips, wafers were only 50 mm in diameter. Today, they are 300 mm and the industry has a plan to advance to 450 mm. Request. It is hoped that this session is going to be useful to you. Please press like button. Please सब्सक्राइब दिस चैनल. यह लेक्चर हिंदी में भी उपलब्ध है. Fabrication of chips. Fabrication of chips on a wafer consists of hundreds of precisely controlled steps which result in a series of patterned layers of various materials on top of another. What follows is a sample of the most important steps in this complex process. Photolithography. Applying photoresist. Photolithography is the process by which a specific pattern is imprinted on the wafer. It starts with the application of a liquid known as photoresist, which is evenly poured onto the wafer while it spins. It gets its name from the fact that it is sensitive to certain frequencies of light, that is photo, and is resistant to certain chemicals that will be used later to remove portions of a layer of material that is resist. Exposure. The photoresist is hardened and portions of it are exposed to ultraviolet light, making it soluble. The exposure is done using masks that act like stencils, so only a specific pattern of photoresist becomes soluble. The mask has an image of the pattern that needs to go on the wafer. It is optically reduced by a lens, and the exposure tool steps and repeats across the wafer to form the same image a large number of times. Resist development. The soluble photoresist is removed by a chemical process, leaving a photoresist pattern determined by what was on the mask. Ion implantation. The wafer with patterned photoresist is bombarded with a beam of ions, which become embedded beneath the surface in the regions not covered by photoresist. This process is called doping because impurities are introduced into the silicon. This alters the conductive properties of the silicon. In selected locations, here we show the creation of wells, which are regions within which transistors shall be formed. Removing photoresist. After ion implantation, the photoresist is removed and the resulting wafer has a pattern of doped regions in which transistors will be formed. Begin transistor formation. Here we zoom into a tiny part of the wafer, where a single transistor will be formed. The green region represents doped silicon. Today's wafers can have hundreds of billions of such regions, which will house transistors. Etching. In order to create a fin for a tri-gate transistor, a pattern of material called a hard mask, that is blue in color, is applied using the photolithography process just described. Then a chemical is applied to etch away unwanted silicon, leaving behind a fin with a layer of hard mask on top. Removing photoresist. The hard mask is chemically removed, leaving a tall, thin silicon fin which will contain the channel of a transistor. Temporary gate formation. Silicon dioxide gate dielectric. Using a photolithography step, portions of the transistor are covered with photoresist and a thin silicon dioxide layer, that is red in color, is created by inserting the wafer in an oxygen-filled tube furnace. This becomes a temporary gate dielectric. Again, using a photolithography step, a temporary layer of polycrystalline silicon, shown in yellow color, is created. This becomes a temporary gate electrode. Insulator. In another oxidation step, a silicon dioxide layer is created over the entire wafer, shown as red transparent layer, to insulate this transistor from other elements. Gate last. Intel uses a gate last, also known as replacement metal gate technique, for creating transistor metal gates. This is done in order to avoid transistor stability problems which otherwise might arise as a result of some subsequent high temperature process steps. Gate last. High K oblique metal gate formation. Removal of sacrificial gate. Using a masking step, the temporary sacrificial gate electrode and gate dielectric are etched away. The actual gate will now be formed because the first gate was removed. This procedure is known as gate last. Applying high K dielectric. Individual molecular layers are applied to the surface of the wafer in a process called atomic layer deposition. The yellow layer shown here represent two of these. Using a photolithography step, the high K material is etched away from the undesired areas such as above the transparent silicon dioxide. Metal gate. A metal gate electrode shown in blue color is formed over the wafer and using a lithography step removed from regions other than where the gate electrode is desired. The combination of this and the high K material thin yellow layer gives the transistor much better performance and reduced leakage than would be possible with a traditional silicon dioxide oblique polysilicon gate. Metal deposition. Ready transistor. This transistor is close to being finished. 3 holes have been etched into the insulation layer shown in red color. Above the transistor, these 3 holes will be filled with copper or other material which will make up the connections to the other transistors. Electroplating. The wafers are put into a copper sulfate solution at this stage. The copper ions are deposited onto the transistor through a process called electroplating. The copper ions travel from the positive terminal anode to the negative terminal cathode, which is represented by the wafer. After electroplating, on the wafer surface, the copper ions settle as a thin layer of copper. Metal layers. Polishing. The excess material is mechanically polished away to reveal a specific pattern of copper. Metal layers. Multiple metal layers are created to interconnect all the transistors on the chip in a specific configuration. How these connections have to be wired is determined by the architecture and design teams that develop the functionality of the respective processor. While computer chips look extremely flat, they may actually have over 30 layers to form complex circuitry. A magnified view of a chip will show an intricate network of circuit lines and transistors that look like a futuristic multi-layered highway system. After all the interconnect layers are formed, an array of solder bumps is put on each die. These are the electrical connections with which the chip will communicate with the outside world through the package in which it is later inserted. These bumps are not shown in the illustrations. When wafer processing is complete, the wafers are transferred from the fab to an assembly/test facility. There the individual die are tested while still on the wafer, then separated, and the ones that pass are packaged. Finally, a true test of the packaged part is conducted before the finished product is shipped. Wafer sort/singulation. Wafer sort. This portion of a ready wafer is being put through a test. A tester steps across the wafer, leads from its head, make contact on specific points on the top of the wafer, and an electric test is performed. Test patterns are fed into every single chip, and the response from the chip is monitored and compared to the right answer. Wafer slicing. The wafer is cut into pieces. The above wafer contains future Intel processors code named Ivy Bridge. Selecting die for packaging. The die that responded with the right answer to the test patterns will be packaged. Packaging. These are individual die which have been cut out in the previous step, that is singulation. The die shown here is Intel's first 22 nanometer microprocessor code named Ivy Bridge. Packaging. The package substrate, the die and the heat spreader are put together to form a completed processor. The green substrate builds the electrical and mechanical interface for the processor to interact with the rest of the PC system. The silver heat spreader is a thermal interface which helps dissipate heat. Processor. Completed processor. Ivy Bridge. In this case, a microprocessor has been called the most complex manufactured product made by man. In fact, it takes hundreds of steps. Only the most important ones have been included in this picture story. In the words, cleanest environment, that is a microprocessor fab. Class testing / completed processor. Class testing. During this final test, the processor is thoroughly tested for functionality, performance, and power. Binning. Based on the test result of class testing, processors with equal capabilities are binned together in trays, ready for shipment to customers. Detail package. The readily manufactured and tested processors either go to system manufacturers in trays or into retail stores in a box such as the one shown here. Request. It is hoped that this session was useful to you. Please press like button. Please सब्सक्राइब दिस चैनल. यह लेक्चर हिंदी में भी उपलब्ध है. This lecture is dedicated to the loving memory of my late parents, Shri Om Prakash Chadha and Srimati Sudarshan Chadha. Maiden name Mohan Dai Suri.